Okay, hello everyone. Welcome back to the Career Catalyst series. We're really excited to have you all join us again for the new year on this exciting topic, artificial intelligence in medical physics. This is a really interesting topic, I think, for a lot of trainees because we really need to start preparing for the future and learn what skills we'll need to succeed in the field. So my name is Ali Khalifa. I'll be moderating the panel today along with Yijing. So Yijing, can I ask you to introduce yourself, please?
Yeah, absolutely. Hello, everyone. My name is Yijing, and I am a first-year PhD student in medical physics at McGill University with Dr. Srinagar, and I'm very happy to moderate this session with Ali today. And we'll have two wonderful speakers and two great panelists as well. Yeah, let's get started. Cool.
So
all right.
Just for those of you who are new here, the Career Catalyst series is a professional development series organized by the COM Student Council, and it's really meant to just help students enhance their knowledge and skills about medical physics and how to succeed within the field.
So just some housekeeping for today. This session is being recorded, as you can see on the left side, top side of the screen, and it will be shared on YouTube. We have our speakers' consent, I think, to record and post it on YouTube. And afterwards, we'll have two 15-minute presentations by Dr. Issam El Naqa and Dr. Sarah Mattonen. And then we'll open the floor up to everyone to ask any questions to our panelists, Luca Weishaupt and Dr. Laya Rafiee. So everyone was free to ask questions, type your question in the Zoom chat and raise your hand. And you can also directly message me or Ali, your moderators, for the question that you don't wish to be recorded, and then we'll say it out loud for you. Great. Great. Yeah, so now is a good time to introduce our speakers. Ali, do you want to go first? I'm going to go first with Sarah. So first we'll have a talk for 50 minutes with Dr. Sarah Mattonen, and so she is an assistant professor at Western University in the Department of Medical Biophysics with a cross appointment in the Department of Oncology. She holds the inaugural Gerald Baines Research Chair for Translational Cancer Imaging at the London Regional Cancer Program and is a scientist at the Lawson Health Research Institute. So she works on her research interests include developing, evaluating, and translating quantitative image analysis tools to support diagnosis, treatment, and response assessment in oncology. We're very happy to have her today, and she's going to be our first speaker today.
Okay.
Great.
Perfect. Thanks, Yijing. Everybody can see that and hear me okay?
Yes.
Yeah.
Okay. Excellent. Okay. Welcome, everyone. Thanks so much for the introduction and for the invitation to speak today. I'm really excited to be here, and thanks to everyone for attending. So today I'm going to give a little bit of a high-level overview of some of the topics that I think are kind of important when we think about AI and medical physics. So Jane gave me some questions to kind of think about as I frame my presentation. So I'm going to really focus on these four going forward today. So first, I'm going to talk about some of the current and future applications of AI. When we're talking about current AI solutions, what's lacking? And then really our goal is to translate these to the clinic. So I'm talking about some of the current barriers to adoption. And then lastly, I'm going to talk about some of the essential skills that trainees might need to start off in the field. So starting off with some of the current and future applications. So I'm going to talk a little bit high level, but I think one of the main current applications of AI is the role of artificial intelligence for contouring in terms of radiation treatment planning. I think this is one of the main areas that's been clinically utilized and is uptake locally, specifically at our institution. This is actually the only AI algorithm that we have in our clinical workflow right now. Limus AI is one of the companies that have developed these fully automated deep learning pipelines for contouring both the target volumes and organs at risk. And this is in use at our institution in head and neck cancer. I think this is going to be a key area moving forward, but I think kind of the next future application of AI is going to be in treatment planning. I think we're going to see a lot of this going forward. I'm sure we'll see a lot of it at COMP this year as well. but how we can use deep learning networks to aid in dose predictions. So specifically, just pulled one example from the literature here, looking at using generative adversarial networks, or GANs, for synthetic dose distributions in the prostate cancer case. So on the top row just shows the original real dose, the dose GANs simulated dose, synthetic dose on the middle column, and then the difference. So I think this is going to be an area really where we're going to have a lot of insight into in terms of when it comes to treatment planning, both in terms of optimizing treatment planning, and as well as looking at being able to compare different plans quickly and saving time for both the radiation oncologists, medical physicists, and dosimetrists. So I think all of these areas in terms of the contouring and treatment planning can have a real impact in terms of clinical workflow. When it comes to other future applications in AI, so I pulled this flowchart from a really nice review article by the group at Harvard in Nature Reviews in Clinical Oncology, really highlighting some of the different areas where I think AI can play a big role in terms of the medical physics workflow. So kind of just going through it one by one. First of all, in treatment decision-making. So I think AI can play an important role in terms of evaluating the patients up front. So determining what might be the optimal treatment for these patients. And these AI algorithms can include, as mentioned here, not just necessarily imaging data, but trying to combine clinical and genomic and other information as well. When it comes to imaging, so specifically for treatment planning and simulation, I think there's a big role to play here as well. We can look at this in terms of both image interpretation, image processing, and registration when it comes to using multimodal imaging for treatment planning. So I think there's a key area here in terms of maybe also improving image quality, suppressing artifacts. So really kind of making our imaging better up front that can be used further down the line for treatment planning. And the third one I won't touch upon too much because I talked about it a little bit already, but I think there's a big role in terms of automated tumor contouring, dose modeling, and as well as prescription selection. So how we can take advantage of deep learning networks, for example, to determine the optimal treatment for these patients. And then after treatment planning is performed, AI can also play a role in terms of plan approval and quality assurance. So when it comes to detecting erroneous events, or especially for highly complex treatments, really AI can play a role in really reviewing these treatment plans pre-treatment and verifying that they're correct. And finally, when it comes to radiation delivery, there is also a role for AI in this aspect. And a lot of different topics can be of importance. So when it comes to image guidance, motion management, even scheduling to improve the clinical workflow. So really, I think it's broadly, it's not necessarily always on imaging, but there really AI can play a big role in all aspects of patient care. And as well, treatment adaptation as well, I think can be applicable to multiple stages of this where it comes to determining who may benefit from adaptive therapy during treatment. And finally, when it comes to follow-up care, the AI tools really can have a big role in terms of predicting response to treatment and identifying radiation-induced toxicities. So I think there's so many different areas where AI is going to have a key role in the future. And then as well, not just necessarily on this flow chart here, but also in outcome prediction. We see a lot of AI applications. This may be at the pre-treatment stage. This could be using during treatment or cone beam imaging or follow-up imaging as well. So not just predicting outcomes, local recurrence, overall survival, but toxicities as well at all the different stages of the workflow that we can consider. So when it comes to evaluating these current AI solutions, I'm going to talk the next two questions really at a high level and hoping to kind of give you a sense of some of the topics that we need to be thinking about moving forward, and hopefully you can use these as a discussion in the panel. So if you have any other questions or more details, we can go into them at that time. So what is lacking in our current AI solutions? So I'm going to go through a list of things that I think is important to think about. So first off is considering the unmet clinical needs. So really we can apply AI to anything, but we really want to make sure that there's an unmet clinical need that we're trying to solve. So this involves working closely with clinician collaborators, either radiation oncologists, medical physicists, to determine where in the clinical workflow that AI can really play a role, because there's no point in doing AI if it's not going to be uptaken clinically or there is no clinical utility need for it. So I think that's what we always need to keep in the back of our mind when it comes to building AI models. Some other things that are lacking, it's very hard, as I'm sure most of you are aware, in terms of building quality data sets to build and evaluate these AI-based models. Data harmonization and curation is a big task in terms of building these models and ensuring that these data are complete. really trying to take into account consistent standards in terms of generalizing these data. So just things to think about. So typically, it can be quite difficult to build large, high-quality data sets. And if we don't have this, then as we can kind of say in AI, garbage in versus garbage out. So we want to make sure that the data going into to train our models is of high quality and high quality standards. So the harmonization and curation can really cause issues with this, as it makes it difficult to curate these data sets up front. And that leads to my next point in terms of the current AI solutions that are out there. Most of these are being developed on really small data sets. So really we need to work moving forward in terms of how we can build and generate large data sets to really make the most out of these AI tools in the clinic. So things to think about going forward is, can we use federated learning to train networks with large multi-center data? So how can we set up the infrastructure to be able to train these models, do transfer learning or continuous learning with these models without having the data to have to necessarily go off site? So can we bring the models to the different centers to kind of keep evaluating that and moving it forward? So how we can work together across Canada and across the world in terms of building these models. And that kind of leads into the next thing in terms of the need for these multi-center studies. So it's really important. A lot of these studies are looking at single institution or single scanner studies, for example, but really moving forward how we can utilize these large data sets from multi-centers to really make generalizable models and tools that can be implemented across different sites. And another thing we want to consider is really, when it comes to this, it kind of comes back to my first point in terms of thinking about the unmet clinical need, is comparing it to the clinical gold standard. So a lot of AI tools we can look at that they perform well, that's great, they're validated, but how do they actually compare to the clinical gold standard? So if it's looking at outcome prediction or if it's looking at segmentation, so what is the current clinical gold standard out there? And we really need to show that the AI tools can advance and augment those current approaches, because really if AI is not adding anything to what the clinicians or medical physicists are currently doing, then there's of no use. So really thinking about the metrics we use to evaluate these models and how we can ensure they're actually showing augmenting performance with respect to what's currently being done. And another thing kind of along all of these lines is there aren't a lot of open source models or methods, and I think we really need to move in this direction going forward. Making sure when we're writing a paper that our methods are well outlined, clearly described, so they're reproducible, and also willing to share the models just so we can work together as a team and being able to evaluate other models and see open source what everybody's been doing in terms of being able to evaluate them going forward. I think this will just lead to the field advancing as a whole in terms of working on some of the above points in terms of being able to validate these with multi-center studies and large data sets as well. And then it kind of comes back to, when it comes to comparing the clinical gold standard, is what else is lacking in current AI solutions. And one of the big things I think we really need to consider is when we're reporting the results of our AI solutions, or how we're kind of moving to implement them into the clinic, is looking at the statistical significance versus clinical significance. So you'll see most of the AI tools that are described are talking about metrics such as the AUC, but most often these metrics don't reflect what's clinically applicable. So really thinking about what is the right metric to evaluate your AI system. So not necessarily the AUC, but what is going to be considered clinically significant with regards to making a difference in both clinical care or clinical workflows. And then one other thing I like to think is important is really understanding when our AI is wrong. So kind of thinking about when it's correct and when it's making mistakes. And this can often be hard to figure out. So I had a discussion with one of our clinical collaborators the other day who was looking at an AI for contouring. And she said it can be hard to figure that out sometimes. And really, we want to know where the AI is making mistakes. We have to think about, are those mistakes being the same kind of mistakes that the human would make? Are they not the same? So just kind of thinking in big, broad steps in terms of how we are evaluating these AI tools, both with regard to their clinical significance, but in terms of where they're making their mistakes and how they're actually correlated to, for example, a clinician in terms of their performance. So really just thinking about how are these models should be evaluated clinically. And when it comes to current barriers, so you're going to see a lot of these topics, I think, are going to be same in terms of what's lacking in our current AI solutions kind of roll over in terms of barriers to adoption of AI in clinical environments. So I'm going to spend the last few minutes talking about some of the things I think we need to consider as we move some of these AI tools into the clinical environment, and things to think about as you're moving into careers as medical physicists in a clinical environment. So I mentioned some of those things that were lacking in terms of small data sets, lack of validation. And I think that's the big key is most of these models are on small single institution data sets. And we really need validation of the models, both internally and externally, to be able to move these into the clinical workflow. So really sharing data, looking at how we can work together to validate models, both on internal and external data. And then when it comes to that, depending on what type of model we're looking at, really thinking about the clinical evaluation. So we've shown that our model does well on our internal data set, does well, maybe it validates on an external data set. But the next step is moving forward in terms of the clinical evaluation. So is there an observer role in your AI tool, whether it's contouring or outcome prediction? So really looking at observer studies in terms of giving your tool to the clinician. How is it going to impact their performance? Is it going to improve the workflow? Is it going to improve their assessment? So really thinking about it, getting it in their users' hands to see how it actually is impacting their clinical workflow. And then that'll just move on to prospective studies if it's showing well in retrospective data, how we can use the tool moving forward on prospective unseen data, and then longer term, potentially getting it into clinical trials, really to show that it has an impact both on the clinical workflow and the outcomes for these patients. And I think a big thing in terms of getting it into the clinical environment is, again, that unmet clinical need, making sure you're working with clinical collaborators and that they're interested in uptaking your AI tools. Because if they're not going to use it and they have no interest in it, then there's really not going to be, it's not going to get into that clinical workflow. So really thinking about that again from a big picture. And then finally, some more technical things that I think we need to think about when it comes to AI adoption in the clinical environment. When it comes to validation, we really want to make models generalizable so that they can work across institutions or across centers. So really taking into account if we're using imaging-based AI models, how different scanners and acquisition protocols can impact things. Also thinking about the data model dependency. So we think high level, different institutions may have differences in contouring practices, treatment techniques, or different protocols or how they contour. So thinking about how that's going to impact getting your model into different clinics across institutions. And then, so that's kind of like the differences in practices. So really just thinking about, it may work at your site, but if you try to validate at a different site who has different practices, that might not always be the case. And we'll always come back to the big interpretability and explainability. So I know a lot of people talk about the AI as a black box. So how we can make really the physicians or medical physicists trust the AI systems is going to be crucial to getting them in terms of their uptake. And then finally, really how we can integrate it into the clinical workflow. So we really need to think about that it's not going to increase time for the clinician users. We want to make sure that it easily flows into their current workflow without too much interruption. And then we really need to think about how we can integrate it as well into software platforms. So just thinking about it high level in terms of that. So I know I'm at my time, but I just want to take last minute or two just to talk about some of the essential skills, I think, based off some of the ideas that I talked about right now. So for trainees, I think you want to collaborate. I think you really need to be communicating with clinicians and medical physicists, really understanding that unmet need of where the AI has the potential to play a big role in the clinical environment. So I think one tip, if I have to give, is to try to be able to, even if you don't do AI as part of your research, is being able to critically evaluate AI methods and papers. So I'm just going to spend the last minute here talking about some things so you can look out for when going through a paper to see if the methods are strong in terms of being able to move that towards clinical engagement. So some things you want to think about is when you're looking at an AI study is the imaging and patient selection. So again, as I mentioned, if it's a single center study and they're excluding a lot of images based on maybe poor image quality, this is really going to weaken their conclusion because that's not realistic of what the clinical data set looks like. If it's a single center, but they've used sequentially enrolled patients with clinical exclusion, that's going to strengthen the study based on a specific clinical question. And multi-center, multi-scanner validation is always going to strengthen the conclusion because you're really taking into account that generalizability. And if it's an imaging-based study, phantom studies or scanner variability studies, such as test-retest, will also strengthen it. When it comes to looking at segmentations, whether it's segmentations for contouring or using segmentations for outcome prediction, we know manual segmentations are often quite variable. So for the single observer manual, that's going to weaken conclusions. So you really want to look for studies with multi-operator validation and really showing reproducible contours. And finally, when it comes to model building and evaluation, I think some things to make sure you're aware of when you're reading your papers. We always want to have a training set and a testing set to evaluate our AI tools on. So if a paper does testing on their training, really this is forbidden, and you can't really trust the conclusions of that model. If they've done cross-validation, this is a good first step, but it does weaken the conclusion. So ideally, we want to be testing on entirely separate data, which the developer has had no access to. So that really strengthens the conclusion. And if we do have a comparison to that gold standard, like I mentioned, that's going to also strengthen the conclusion. And if we're looking at outcome prediction or radiomic studies or that sort of thing, if we can show some biological meaning or relevance of some of the features that we see on imaging, this is also going to strengthen the conclusion. So just some high-level things. I know I went through this very fast, but in terms of thinking about when it comes to both model building and evaluation in terms of how we design these studies, to think about going forward, because I think that's the key, is we need to move these studies from the labs into the clinic. So thinking about what we can do along the way to improve that. So I think AI is going to have a big role in medical physics going forward. So I hope we can discuss this more in the discussion panel session. So thanks so much.
Great, thank you so much. That was a great presentation. There's definitely a few points we'd love to talk more about during the panel discussion. In the meantime, I'll introduce our next speaker. So Dr. El Naqa is the founding chair of the Department of Machine Learning at the Moffitt Cancer Center in Tampa, Florida. He is an internationally recognized authority in fields of machine learning, data analytics, and oncology outcomes modeling, and has published extensively in these areas with more than 220 peer-reviewed publications and 4 edited textbooks. He has also been a member and fellow of several academic and professional societies, including the AAPM and IEEE. So please welcome Dr. El Naqa.
Thank you very much, Ali, for the kind introduction. Thank you, Eugene, for co-moderating this. Luca and Leah, I look forward for the panel discussion. Of course, it's always a tough act to follow Sarah in any presentation. So let me just recap a little bit and start by what is this acronym that we typically use, AI, ML, and DL. They are typically related in this Venn diagram, which is practically it shows the interrelationship between them. Artificial intelligence is more about the systems, could be the hardware and the software together. Machine learning is the computer algorithms, the brain that drives the AI system itself, and deep learning, as probably you know, is a subcategory of machine learning that deals primarily with data representation. The most focus is going to be on machine learning, because these are the computer algorithms, pretty much what we work with in terms of our type of development. Now, these algorithms can be divided based on the text into supervised, unsupervised, and semi-supervised, depending on the degree of labeling of the data. Most application in medical physics probably falls under this category of supervised learning, though there are some applications that uses unsupervised learning. And currently, because of some of the issues that Sarah already mentioned, semi-supervised seems to play also a growing role in the field. Just to make the clear distinction between deep and conventional machine learning techniques, it's about data representation. The feature extraction, feature selection can create bias. Deep learning seems to resolve this problem by creating a single framework that can combine these steps together. This is an example from diagnostic PET-CT images, extracting a region of interest, and you learn the data representation through these convolutional layer and pooling layer. Convolutional layers is doing the feature extraction, the pooling layer doing the feature selection. Then you apply your favorite learning task, for example, in this case, classification being malignant or benign. Now, question, why we should care about AI for medical physics? There is a clear motivation in terms of medical physics involving large set of processes spanning consultation, treatment planning, large amount of information, human-machine interaction, optimization, and more importantly, many steps of decision-making. Methods based on machine learning can identify patterns and complex relationship between variables and processes. They can also generalize to unseen experiences. So there are two main type of applications if we look at radiation therapy. There is automation, quality assurance, treatment planning, motion management. These are some examples, as well as personalization of treatment, potentially patient outcome, not one hat fits all, but a defined prescription for each patient. And of course, modeling response, whether it is at a conventional setting or a more adaptive type settings. I should key this one in that medical physicists have been pioneers in AI. So it's not a new topic for us people working in the medical physics field. AI work in medical imaging started in the 1960s, primarily areas related in diagnostics, as well as in therapy later on. That goes some late to mid 90s as well. Some of the major contribution that medical physicists made to the field of AI is in standardization of data. DICOM is a key example of that. There is currently a lot of struggle in characterizing other data aside from the imaging data and how you can represent that meta information. Development of rigorous evaluation tools that are currently used as a standard for ML classification problem, ROC curves. One example Sarah already showed was developed by a medical physicist at U of Chicago. Building reference standards for images, for example, synthetic data phantoms in order to conduct proper evaluation. These are also key contributions. So the future is bright for medical physicists to continue along this journey. This is just showing representation where AI applications happening in the radiological sciences. As you can see, it's growing on an exponential scale, probably more in radiology, more than radiotherapy. But I mean, I think in our field, we are actually catching up. This is similar to the workflow that Sarah has shown, showing the different steps. And along each of these steps, there is an application, maybe more than one application of machine learning or deep learning techniques. This is a snapshot about how these are currently evolving. Probably mostly has been conventional machine learning techniques, but deep learning techniques are probably taking over at an exponential growth rate as well. Some sample applications from what was shown before, and also Sarah mentioned several of these, is auto contouring. It's probably a prominent applications, and this is one example of that from the DeepMind group. Treatment planning, radiation dose prediction using these kind of techniques, pretty much bypassing the whole physics chain along the way. Quality assurance is another example, and this is one case where we are looking at unsupervised type learning techniques, try to recharacterize some of the task group metrics that are used for evaluating failures. Another set of applications that areas we work on is related to imaging biomarkers, a field of called radiomic, looking, for instance, in liver cancer prediction. Outcome modeling in case of lung cancer, looking at outcome not only by imaging, but using other biomarkers coming from molecular biology along the way, such as cytokines, microRNAs, and SNPs, to name a few of these. Now, once we have these prediction models, we are able to do this adaptive radiotherapy, which is pretty much personalizing how the treatment should be delivered and making modification along the way. So if there is a change in the geometry, we can modify the treatment plan, maybe also escalate or de-escalate the amount of the radiation fraction being delivered in order to ensure we have the best outcomes in terms of local control, mitigating toxicities. To facilitate translation, there need to be also development of software tools. These software tools can serve different purposes. Some of these different purposes, obviously the application itself, but as well as investigating this relationship between these algorithms and the user they are using, implementing them. This is two examples from one of our research associates, Dr. Nirwala, developing a recommender system for adaptive intervention in radiotherapy. The other one is related to image interpretability, especially when you are dealing with multi-institutional study. And that's what used the notion of federated learning that Sarah also mentioned. This is being developed by Mrs. Gore in collaboration with other groups as a part of a consortium called MEDRIC, shown here. Now, one of the key issues when you are developing software for AI that's different from conventional software is the user factors here are different. You are seeing decisions made by these algorithm, and you would like to assess whether these decisions are acceptable or not, which is a major differentiator from traditional treatment planning softwares that we used in medical physics. Now, as mentioned earlier as well, AI is nothing but perfect. There are many examples highlighting bias, uncertainties associated with the implementation of these algorithms, where in the public health domain, there are several of these examples. Most recently is that epic sepsis model was implemented as part of the electronic health record in several institutions, and turns out the performance that was promised in the initial development was not what was observed in a clinical practice. Now, in the medical domain, there are many examples as well when these algorithms had learned something different from the intended goal as a human when we are using this algorithm. One example is that skin cancer risk prediction, the algorithm is looking at a ruler and using it. Obviously, anybody with a very high risk of skin cancer, there would be probably on their slide, there might be a ruler, and that's what the algorithm was captures. Prediction of lung disease, another example where the presence of the tube is what the algorithm honed on. And of course, the implementation of AI in the era of COVID-19 was not as initially promised, and these methods resulted in many conflicting results. I mean, begging the question about issues associated in their not only development, but also deployment. So key components are data quality and context matters. And this is also something Sarah touched base on when we're dealing, for instance, with imaging and harmonization issues along the way. Some of the requirement reliability for of AI in medical physics is how we can refine that life cycle of AI development, starting from the discovery, early cohort, early AI application, population-based study, then the market launch. When regulatory institutions get involved, and whether this is actually a one-time mark or it's actually a continuous life cycle is actually being debated, especially when we're dealing with issues related to law and regulations and ethics. Obviously, there are issues to address in terms of diversity and whether the cohort is being represented, the independent data validation process, transparency and availability of these methods and data being used, ethics when applying these techniques, and reproducibility is keying for achieving any form of credibility, as well as having quality assurance type of programs like we have in any other medical physics application that is also a necessary requirement for successful implementations. Now, one of the questions for you when you have a machine learning applications and you would like to implement that algorithms is what sample size I need. In generic statistics, I mean, there are, power analysis, and you can estimate that. In case of machine learning, it tends to be a little bit more complicated, but ultimately what you are trying to achieve is a relationship between bias and variance and finding this sweet spot between them. Currently, what's used for that, what's called the learning curves representation, when the errors associated with the training set, as well as the validation set plateau. So it's more of an experimental type of approach. There are some theoretical work, and of course, that's an area that is need more expertise, more interest probably from you in order to enrich how we can come up with formalisms that we can use for assessing what would be an optimal sample size, for instance. Now, once you determine what's the sample size, you need to select an evaluation plan for the machine learning algorithms. That can consist of two parts. One, what are the measures that we are going to use? We mentioned earlier ROC, area under the ROC curves, root mean square error, divergence. That depends on the nature of the problem you are solving. Sometimes we use generic metrics, and we have to be careful about that, especially with specialized application, that this metric may not be representative. Sometimes image segmentation is one example of that. It's just using a simple dice metric does not necessarily meet the clinical criteria, for instance. Other than that, there need to be multi-level validation when you are developing that model. There are several statistical resampling techniques. Probably cross-validation is the most common one. Bootstrapping is another approach, which are necessary during the development to ensure that the algorithms is actually trained and learned and did not just memorize the data, which can potentially happen with these complex techniques. There is ways for AI machine learning validation. There is the tripod criteria and its offshoot tripod AI that gives you multi-criteria levels. What would be the level of evidence required in order to ensure that this algorithm is actually performing to the expectation? That can start by internal validation, cross-validation, for instance, as well as independent data set for external validation too. And there are several checklists associated with that. Almost every society has their own checklist, starting for the Imaging Society. For example, they have a claim, and in the medical field, there are my claim and so on. There is the consort for clinical trials. And in medical physics, there is what we call also the clamp, which I touch base on. Another important criteria beside the accuracy validation is the ability to understand what the algorithm has learned, and if we can relate to that in our application. Talking a little bit about the checklist for AI ML in medical physics, I came up with the acronym CLAMS, and probably it wasn't initially intended, but this is how it turned out to be. And this is the current criteria. This is a working group at the American Association for Medical, the AAPM, and probably there are other groups working on similar checklist for different areas related to medical physics, diagnostic, radiology, and so on, as I mentioned earlier. Now, some of the points in this criteria is, this is for publishing purposes, of course. It's the clarity about the purpose of justification of AI machine learning in the algorithm selection versus whatever other techniques that could be available. Clarification about the data set characteristics in terms of acquisition, size, partitioning, and the 3 T's, training, tuning, and testing. These need also to be carefully mentioned in any of these papers. Description of the machine learning methods in terms of optimization, loss function, augmentation, regularization, as well as the performance criteria and the type of validation, internal, external. Important also to add in any of these publications, the significance of the results, interpretation of the performance of the machine learning techniques, and what actions can be used in order to utilize this tool in a clinical practice. Currently, if you go to the medical physics website and you would like to submit a paper on artificial intelligence, these are the questions based on this criteria that you are going to encounter. And it's important to address each one of these questions on the checklist, otherwise the paper will not go through the review process. And other journals that Sarah and I are involved in trying to develop something similar to this as well. So this is in terms of publication and how we can pass that process, but that's one step along the way. There's also the requirement for interpretability, as I mentioned earlier, and there are this phenomena of that Machine learning techniques that are complex, like deep learning, tend to be more accurate but less interpretable. But decision trees tends to be simpler algorithms, less accurate but more interpretables. And in that regard, I'm going to show a couple of examples on interpretability using some of the more common techniques. For instance, GradCam, which is looking at gradient variations in the different layers. This is an imaging example trying to predict survival, and it seems the algorithm identified certain areas within these CT images. And by asking our radiologists what is it that algorithm is looking for, turns out to be cirrhotic, which is kind of inflammation, which affect liver disease and potentially that could lead to cancer. So the algorithm honed on something relatable. This can become a little bit more complicated when you are dealing with multi-omics data. It's not only images that we can visualize, but data that can be clinical data, the symmetric data, and biological data. So there need to be some innovation in that area that's still maturing as we speak. Of course, I mentioned the quality assurance and how we can implement AI in the clinic. I think there is a template to do that in the medical physics world. I mean, how we accept actually software or hardware. There is an acceptance testing process, which is you match what the vendor has given you. There is a commissioning, how you can take an algorithm, tailor it to application in your clinic, having a quality assurance procedures. We do secondary type measurement, as well as the continuity of that type of program to ensure safety when deploying these type of algorithms. These are some use cases and some ideas. This is being currently formalized in more of a task group type approach in some of these societies, whether here in North America or in Europe. I'm a strong believer that the combination of quantum information theory, some basic physics with machine learning can drive robustness of these algorithms. These are some of these ideas that we worked on, whether for treatment planning, image guidance, or clinical decision support. And I think this is an important and emerging area that combines both the skills of the physicist as well as the computer scientists in each one of us. So some of the take-home messages: AI/ML offers new opportunity to develop better understanding of medical physics, radiation oncology processes, and improve their workflow. That boom is this big data give us all kinds of opportunities, but also advances in hardware and software has enabled this compared to years ago when somebody like me started in that field. AI/ML is going to touch every field, every area of our practice, especially medical physics, and I think we are the most AI-ready group in order to embrace its advancement in the field. This is some of these recommendations: how you take an AI/ML algorithms, ensure you have the right sample size, do the evaluation and validation, as well as making sure that you adhere to ethical AI standards, which is the afterthought when you have an algorithm, but need to be actually at the front end rather than at the back end of AI implementations. Of course, I re-emphasize that point that medical physicists have been pioneer in AI application and in medicine, and they will be also the major contributor to lead its safe and beneficial application, not only in medical physics and radiotherapy, but as well as in the general biomedical domain as well. These are some references. These are some websites that many of you probably already familiar with. And I would like to end up with this quote from Professor Hinton, which is always a tricky business to use some of his quote, but I think this one right on point, that he quote Max Planck saying, "Science progresses one funeral at a time. The future depends on some graduate students who's deeply suspicious of everything I have said." And that's how we look into the future. This is our group here at Moffitt. And of course, once you are finished your graduate study and you feel you would like to do a postdoc with us, you are more than welcome. Thank you very much.
Thank you very much, Issam and Sarah. So we'll open the floor for all questions now. And actually, now is a good time for us to introduce our two panelists today as well. So Luca and Laya, would you like to introduce yourselves? I could also introduce you since I know both you guys, but go ahead, Luca.
Would you like me to start?
Yeah.
Sure. Hi, everyone. My name is Luca. Really good to be here and see some familiar faces. For those of you who don't know me, I did my undergrad at McGill University. I had the immense pleasure of working for Dr. Shireen Enger and amazing people such as Yujing were my colleagues. And after my undergrad, I started a PhD here at Harvard and MIT. The PhD is in medical engineering and medical physics. I'm currently doing a bit of research in health equity. So I can provide some insights into the world of AI and medical physics and what it's like to be a student working on projects like that. During my undergrad, I did research in a lot of contouring of tumors and medical devices. And Yujing and I founded McMedHacks, which is a deep learning series and a hackathon on applications for medical image analysis with deep learning. So happy to talk about that as well. Yeah.
Thank you, Luca. Now we have Laya, who's also joining us as a new postdoctoral fellow, who's a computer scientist. Would you like to unmute and introduce yourself?
Yes, thank you. So I'm Laya. I actually recently finished my PhD from Concordia, actually not from a medical physics background, so I'm a computer scientist. My major interest is actually about anomaly detection, out of distribution detection, domain adaptations. I have a little bit of work on medical imaging as well. So I recently joined Shireen's lab, and I'm happy to be here. Thank you.
Thank you, Laya. Yeah, so now is a good time for everyone to ask questions. We have any questions, or you can also raise your hands. Ali, if no one's asking a question right now, we can get it started and get everyone started.
Yeah.
We have Jose. Jose has a question. We're sitting in the same room currently. Okay, go ahead.
Thank you so much for the talk. I was just like, it's a more general question. So noting that a lot of the innovation in the AI, like not just medical physics, but like in general AI, they come from the industry partners, like, Facebook or DeepMind. Do you foresee a future where like companies in medical physics that work on AI get to do such innovations and like share codes the way they're sharing codes? And like, where do you see the role of the private partners in the future of medical physics and AI? And that's like a general question, like Issam or Laya, or Sarah, like it's a general question, so you guys can answer. How do you see it?
I'm happy to take it, Hussein. Thank you very much. This is actually a great question to ask. I probably other member of the panels who can further chime in. You are spot on in terms of the main innovation came from the high-tech industry, Google, Amazon, and maybe not Microsoft at the beginning, but later on. And that success came when they made the decision to make their tool open source. And that wasn't the beginning. I mean, that was part of that BrainX project, that they found that in order to be beneficial and to use these tools, if you make it more open source, other people will chime in and bring their own knowledge. And this is kind of the evolution we have. Google came up with that ImageNet, which also gave you kind of an evaluation validation data set that is, a million natural images, million plus probably, which is something we actually still need in the medical domain. But I'm not sure how to state this one correctly. They didn't do it out of good heart only. There is a financial incentive. There is benefit from building these tools and having others crowdsourcing in its development, which is a vision that probably was not clear in other industries as it was clear in the high-tech industry. It helped that many of the scientists who were involved in this, they all believe in open access, open source, and to this case. But I don't know if it's going to happen in the medical physics field or radiation oncology being a smaller market, but definitely there is a benefit for creating a similar parallel in terms of allowing everyone who has ideas and innovations to apply their tool, test it, and evaluate it, as what happens with ImageNet, with AlexNet, and all these things that spur the field again. We currently here institutionally, actually, because we work directly in cancer research, we get approached with some of these companies that they would like to partner. And the reason for that is not that they think we can develop better tools, but because we have domain knowledge related to cancer treatment, cancer workflow that can be helpful for them. So working together may be one recipe of making this transition into better development and better implementation, and hopefully more open source kind of mentality too, which is Sarah already emphasized in her talk too.
Thank you so much, Issam, for your great answer. Does anyone else have some opinions on this as well? I think Sarah, you, or Issam, you mentioned Madirect. Oh yeah, sorry, Laya, go ahead.
Yeah,
go ahead.
I just want to add something about why, like, what are the barriers actually private sectors might have to compete with like big tech companies like Google. So one of the first things is that computational resources, unfortunately, like private sector, smaller company doesn't have that much of computational power that the big companies have. And I think many, like, I'm not going to say like all the good researchers goes to those big tech, but unfortunately, there are a big majority of like researchers that try to go to bigger companies, which is like actually not very beneficial for a smaller company. So I guess these two are major barrier for like these smaller companies, like to be able to compete with this big company.
Thank you,
I
Laya.
think another big barrier to sort of moving the field forward here is just the availability of data and the way that people in the medical profession handle their own data, where they're sort of stewarding it as an asset, right? A lot of physicians will have their own data sets that they will use for their own publications. And once you've published something, it's very rare that the data sets get published in this field, right? And that's something that's very different in other industries. And I think to really make great strides there, people's mentality on data availability has to change a lot, and policies are being changed, at least around here, that forbid this sort of like coveting of your own data. But I think there has to be a lot more change.
Absolutely. And I think both Issam and Sarah mentioned about, multi-center studies, and a lot of the studies that's been published by now, if it's single center, the conclusion weakens. However, from a very practical point of view, there's a lot of, when you're trying to summon a bunch of institutions together to all work together and do multi-institution studies, is a lot of barriers, such as with data sharing, so that approaches like federated learning are being explored right now. However, I was just curious about, both Issam and Sarah, if you, in order to fuse or to form this kind of nice collaboration for multi-center institution studies, what are in your experiences on getting people on board? What a good advice to getting people on board to collaborate for multi-center studies and just make things happen, And then after that, I'll start asking questions from the audience as well.
Sure, I can start, Yijing. That's a great question. Yeah, I think it's really important. I think having those clinical collaborators at multi-centers is really key. I think for our experience, we usually can get them on board in terms of if it's a question that they're interested in or a clinical area that they have interest in. But really the challenge does come down to when it comes to the actual data sharing part. I know specifically at our institution with the data sharing agreements, just getting the data moved is usually the struggle. So I think really, like you said, the federated learning, I think we need to think about how as a field we can move forward where we can maybe keep our data at our own sites and how we can best work together to build and evaluate these tools, but kind of optimizing that workflow. Because I think it's the data sharing is slowing us down moving forward. So I think usually get the collaborators on board, but yeah, it's a matter of getting the actual pipeline end to end.
Yeah.
Right. And one question I have as well about this topic is, a lot of the research in AI, in the AI field right now, we see a lot of things coming from these big companies like GPT, that are really these enormous models that require a lot of data and a lot of computational resources to train. So do you find it maybe a little discouraging when we're thinking about medical applications that this is the direction that the AI field is heading in?
I was waiting for somebody to mention ChatGPT, so thank you, Ali.
There you go.
So, as you know, ChatGPT is trained on the internet, probably the open source internet, Wikipedia, or other resources like that. Now, there are two ways to look at this. It's good that there are training happening on the large open internet, and as well as in the medical imaging domain. And as you know, there is, many of you know, there is transfer learning is one way that helpful as a technique in taking domain knowledge from one area to another. But it is insufficient. That's a reality, because the type of problems we face can be very peculiar to the degree that makes transfer learning not obsolete, but less useful as it is in some other areas. So creating data resources that allows doing something like this is not unobserved by major institutions. One of them is the National Institute of Health here in the US. So MEDRIC is the Medical Imaging Resource Consortium, right? The idea of that was, it's $20 million, $30 million actually endeavor to bring all these institutions to donate their data sets to a single central repository that is actually housed at the University of Chicago currently. Because what you need is to create that benchmark. Sarah mentioned it, the need for creating a benchmark. That cannot happen with a federated learning framework, because there are some challenges there. But if you have this incentive to donate images, which is what's happening in that MEDRIC, and we would like multiple MEDRICs, not only one MEDRIC for this COVID type data sets, then you will have more options for benchmarking. Then you can do training on federated learning there with multiple institutions that, you can bring like-minded people together. Then you have a benchmark, and that's why the need of such resource. Now, there are other initiatives from the NIH, like the TCIA that many of us use, the TCGA, CTEP, and you can name many of these things. And there are similar ones happening as well as in Europe. But this is not everyday clinical practice data. That's a different story that probably approaches on federated learning. When it becomes mature, you can solve. With federated learning, there is another package that need to also be careful of it. It's not a straightforward implementation as we've experienced ourselves. You have to deal with IT, cybersecurity, and all that other stuff. You have to create an infrastructure that convert the information you have to a common format, a DICOM-like type format, if you wish, in order to facilitate communication between these different institutions. But I think people will come to the realization we need each other to do some form of crowdsourcing in order to solve bigger problems related to healthcare applications.
Thank you, Issam. Ali, do you want to get us started with our audience questions now?
Yeah, for sure. So we do have a few questions in the chat. So the first one is from Jafar, who asks, as the most cancers are known to occur by random mutations, my question is this, can randomness be predicted using AI by a mathematical model? So I guess this is going into the area of risk prediction and even using AI as a preventative technique. Any thoughts on this?
Can you give more clarity on the question? It is a random mutation, but it's driven by some genetic factors. So it's not totally random. It's more of stochastic process versus being random out of it. And there are models that can be used for understanding what are the genetic drivers for cancer. And modeling stochastic behavior, it could be done in different ways in machine learning, actually. There are these Bayesian neural networks or Bayesian network type techniques. They are inherently probabilistic. So that's one of the approaches that you can handle randomness. I'm just giving one example. There are many examples. Generative models by its own natures uses stochastic techniques as well. But pure random, a uniform distribution, no, nobody can predict that. It has to have some formalism. It follows some kind of predictability in terms of probability that you can handle. You can predict a Gaussian distribution, you know, what's the mean and what are the variance, but you cannot predict a uniform distribution unless you are looking at where the ranges are.
Great. I hope that answers your question, Jaffer. I see Courtney has another question. Hello, Courtney, you can also ask this question yourself, or I can also read it for you. So Courtney is a postdoc working in the field of nuclear medicine. He's not currently working in AI, but is very AI curious. And in many or most of the AI talks he's seen, including during McMahon he has found an emphasis on external beam radiation therapy. His question is, are there notable resources for physicists in nuclear medicine, particularly, who would like to explore AI? Image data banks, for example. I think if you're talking about public image data sets, what Issam mentioned, TCIA, TCGA, they're good public data sets. And then is Madric publicly available?
Yes, it's public. Yes, it's also a public resource. Yes.
And then is there anything else that's more particularly for nuclear medicine that we can suggest for Courtney?
I want to make that statement. One of the first papers published for radiomics with therapy was actually using PET images, because PET images are unique and very informative in terms of the knowledge that they can provide. Of course, CT give you anatomy, but PET and SPECT and all the nuclear medicine give you function, which is what you would like to know as well when you are trying to model response. Available data sets is what you mentioned about the TCIA, but there is another source that you can also tap in, but it's by request, which is what's called there is a network of I'm talking primarily in cancer. Of course, there are other applications. There is a network of cancer centers, national cancer centers networks that held multi-institutional data that is stored as part of clinical trials, and it has to be requested, these kind of data, and you have to apply through it. An example of that is called, throwing too many acronyms now. It's called
Maybe you can send the link in the chat.
Yeah, I can put it. ECOG Akron is one of those. It's not always the most responsive group in the universe, but you can always try and check if they have something relevant to your studies. And if you are persistent, they will respond to you. But they have multi-institutional clinical trials, imaging data set, specifically speaking, across the board, PET-CT, MR, you name it. And some of it is open source already. You can find it on TCIA. Aside from the TCIA, there is something called the data commons that the NIH is actually building, that not only the imaging data as well, but as well as the clinical data and potentially biological markers related to that. I'm going to put the data common thing website. It is still under development, but they are very much interested in harnessing clinical trials that are sponsored by the NIH, making it available for the users. And some of it is publicly available, totally publicly available. Some of it you have to make a request.
Great. Thank you, Issam. I just put in a few for data commons and also TCGA, TCIA, and also Google has something called dataset search, where you can search any sort of data set as well on there. So, and then Madrick is obviously another great resource as well.
I can put the link for Madrick too.
Yeah, I actually saw their booth on during APM last year. It's great.
Okay, perfect. Yeah, I mean, the mandate for that group is to make the data available, so they have to do that.
Yeah. Okay. Oh, we have someone raising their hands. We have Zara raising your hand. Please go ahead and unmute. Not sure. Oh yeah, go ahead. Great.
Yeah, hello everyone. My name is Jair. And well, I am actually a physics student, undergrad, from Peru. And my question is, well, I want to know how I can introduce in physical medics, or in this case in IE for medical physics, because I don't finish yet my undergrad, but I want I know I want to be medical physics. I want to work in medical physics. So my question is how I can introduce myself in medical physics. That is. Thank you.
Thank you for your question. I think Luca will be perfect to answer this question since he started as an undergrad and did AI in medical physics. Go ahead.
So the question, my audio is sort of cutting in and out there, but the question was, how do you go from a physics undergrad, how do you transition into medical physics? Is that correct?
Yeah, I think so. And also how to get onto AI and medical physics projects and so on and so forth.
Yeah.
Just give a few words.
I can give my story as one data point. But for me, it was a matter of pretty early out, just like reaching out to people that are in medical physics and getting a sort of sense of where there are opportunities to do some good work, because you'll find that many labs are actually looking for people with exactly this interest. And so I think a very sort of direct way of starting to get into medical physics is just to do some research in it in a lab. And that's the route I went. You can certainly go from a physics undergrad into a medical physics master's program. I'm sure there might even be some people here apart from me that have done that. But it helps you a lot in terms of like, you know, getting in and just having a network to be working in the field before it's time to apply. So that's what I'd say. And in terms of like learning the necessary skills, I never had any sort of formal education in medical physics or anything medical related for that matter. So I was a pure physicist going in. And the medicine, you're sort of taught on the job, the necessary skills there. And it helps, of course, a lot if you are the type of person that will go out and just sort of learn as much as you can from the resources that are available online, not just for the sort of medical aspects of medical physics, but also the technical aspects of machine learning. There are great resources out there already, not to only plug ourselves, but like Stanford, for example, has really good resources out there also that are all free. So there are many ways of sort of trying this out before you buy, and that's definitely what I would recommend.
Thank you, Luca. And Laya, I'm curious, did you have a similar path as well to AI and medical physics? Were you more on the AI side first or a medical physics side first?
Are you talking to me?
To Laya.
Okay, Laya. Laya's go ahead.
Yeah, actually, in my master, I actually was on the machine learning. It was mostly on graph theory. So, as previously mentioned, so networking was one thing that like lead me towards like coming into AI, because I was interested in, but I couldn't at the time in master. So the same thing happened in my PhD. So my PhD was mainly on general deep learning, but I also touched a few on medical background. So I think like going to different talks, talking with different people, seeing the needs that you can use your knowledge in other areas rather than the like computer science, and like talking with a lot of physicians. I had like a course at McGill that we had to work with different clinicians. So that's where I found like how I might be able to use like the knowledge that I have in other areas, like in real applications in medical. So talking with different people, using the resources, as mentioned, like caused me actually like pushed me toward coming in this way.
Thank you, Laya. I'm curious about our speakers' paths too now. How about you, Sarah and Issam?
Yeah, I can start. So yeah, I kind of didn't move into the field of AI. So I actually trained as a radiation therapist to begin with, and then moved to graduate school. And that's where I kind of gained more experience with AI applications in terms of applications to medical physics, which was great. So kind of took me in that path, but I agree with everything Luca and Laya said. I think in terms of an undergrad coming through is, yeah, just taking advantage of the resources out there. There's tons of online courses, talks like this, the McMed program, things like that, that kind of can get you involved early and kind of get you aware of what's out there in the field, and don't be afraid to reach out to different groups that are doing research that you might be interested in, and try to get involved as early as you can, and just being aware of that career path, what you need to kind of get to long-term goal if you want to be a medical physicist.
Well, in my case, it's pure random walk, Brownian motion. That's how I got to the whole thing. Was doing image analysis at the beginning, and that was before AI was even popular. Actually, there was a lot of people who were skeptic at the time. But the only methods that I found that can work in these applications with AI-based techniques, albeit being more conventional than what's currently being used today. Another random walk got me to the medical physics field because I was looking to get into medical domain, and I was lucky to meet people that introduced me to the field just by pure coincidence. And the idea was, if you go to biomedical applications that are not necessarily medical physics, you probably do a lot of medical applications, but you will never see a clinic in your life. And that was the argument that in medical physics, we actually work in the clinic. And that's kind of a major advantage that was very intriguing to me. So this is how it happened.
Great to hear you guys' stories. So we have another question from Jigar. I'm not sure if I pronounced your name correctly. I'm sorry if I'm not. So thank you for the talks. This was very interesting. Given that medical physicists have made important contributions to AI development, what do you envision the future role of clinical medical physicists as AI becomes increasingly implemented and has the potential to automate many aspects of the day-to-day responsibilities?
I can start. This is a very common question, but I think a lot of people overestimate how good AI is at this point. We're nowhere near like automating anybody's job in the medical industry. AI remains a very interesting tool with a lot of potential, but it's still rather dangerous, and you will not be out of a job anytime soon if that was the underlying question. If anything, eventually you're going to get tools that are smarter and will still very much require your domain expertise to validate that they are working correctly.
How about, yeah, go ahead.
I will be more harsher than Luca on this one. I mean, I did mention Jeff Hinton, and he made a quote that created a lot of controversy with regard to radiologists, that radiologists in a few years will have no job because of how deep learning is good in understanding images. But the counter argument for that, I'll put it in the context of medical physics, that it's medical physicists who don't know AI will have no job. Medical physicists who know AI will secure the future and develop AI for the future.
I'll ask my follow-up question after everyone finishes. Go ahead, Sarah.
Sure. Yeah, no, I was just saying I completely agree with Luca and Issam. I think it's how medical physicists best work with AI to optimize workflows and that sort of thing. And I think it'll, as Issam said, be interesting to see how curriculum changes and training changes as AI becomes more popular, and just thinking how that needs to be implemented in terms of either graduate or residency programs, in terms of, like Issam said, making medical physicists aware of AI and who know AI, and how that's going to be implemented into the working environment.
Go ahead, Laya, if you have something that you would like to say as well.
I just want to say, like what Luca said, I agree on that. I believe AI is like an infant right now. So there are a lot of room to improve, and there are a lot of actually drawbacks of the AI. We don't know it yet. So we have to work on that. And you just have to see AI as an assistant, not just something that replaces you.
Yeah, I absolutely agree. So here's my follow-up question. Since we talked about a little bit about the future training of future medical physicists and the AI integration into all of this, and there might be changes in the future about our medical physics curriculums and how medical physicists need to work with AI in the future. What would you suggest everyone to do who are currently trainees that they should be mindful of going into the field, even if their research focus isn't on AI projects?
I think you have to learn AI, and radiology is part of the curriculum already. And in medical physics, we have to do the same. I know it's a busy curriculum. A lot of people can argue about that, but it has to find a place.
Yep.
Can I ask a follow-up question to you directly? This is also referring back to your last one, but when you say know AI, do you mean know how to use AI, know how AI works in broad strokes, or do you mean be able to program AI?
Oh, this is great. I mean, I wasn't clear. It's a know-how knowledge. Not everyone needs to be a programmer, but at least understand how these algorithms operate, function, used, and try to interpret what these algorithms are doing. Like for treatment planning, any of us can understand what this algorithms, whatever algorithm, what it's doing, what are the results, I can explain them. I don't have to code a treatment planning system.
Yeah, in that case, I absolutely agree. Like this being here is exactly how you're preparing yourself for that future and seeking out opportunities like this if they're not already part of your curriculum. But I mean, the world of AI is shifting rapidly as we're seeing now with those large language models, and just sort of, you know, keeping up on, like, you don't have to, like Issam said, know how to create all these things, but at least have a broad idea of what's out there. That'll be super helpful, especially knowing the drawbacks that AI can have and the real dangers. Even when things make it to the clinic, they can be super dangerous. You should know like the strengths and the potential pitfalls of the tools that will fall into your hands sooner or later.
Yep, I absolutely agree. Thanks, Luca. Thanks, Issam. Yeah, do we have any other questions? A simple addition. There will always be new problems, so there will always be an urgent need for scientists. This is from Jaffer. Let's say this is your name correctly. Anyway, yeah, absolutely agree. I think that it's more of a assistant collaborative tool that if you have to, we have to as a whole field know how to use it, at least to be able to have this language going on to collaborate with others. And then obviously I think medical physicists as a whole profession is standing at the cusp of understanding the technology and having the skills to program and to invent and innovate in the algorithmic side. But even if one specialty isn't quite AI or on the programming side, we still have to understand the functioning of this side of things. But we still have to be cautious. And before all of that happens, we have to the research part, obviously, the implementation into the clinic, we have to be very cautious about what we're seeing and what we're using. And very rigorous quality assurance needs to be implementing and so on so forth. Is there any follow-up questions from Ali?
Yeah, I think a lot of the questions that have been answered today.
We have another one from Sahid.
Audience.
Yeah.
Sahid.
Please go ahead.
Yeah, good day, everyone, and thanks for the enlightenment and the lectures. I want to ask a question for those who are new and have a strong interest in this area. Are there resources, or do you have? Can you organize trainings, perhaps later, that people who are interested in this area can, you know, join people who are in the forefront, and then you take them through, because there's always need for, you know, for mentors when you want to have a good training in a particular area. So just reading everything up and down might not give you the sound knowledge as you really require them. So what if you have people who knows what is required, so they can easily give you the way. So some of us who are already having a PhD, we have interest, but might not know how exactly how to really go into the area. So if you have resources, or you think there are trainings that could be done on this, so I'll be happy to know this. And the second question is the second to the last slide that you showed. I'm talking about Prof. Issam now. So there are some things I needed to capture. There are some resources if you can show that second to this last slide again, it will be good to. Thank you so much.
Oh yeah, I'm happy to share the slides if it's okay with Eugene and Ali. I can just send them a copy.
Yeah, of course, we can arrange that. Okay, so I don't see any more questions from the audience, so I think we'll wrap up here. Thank you so much, Salam, Sarah, Luca, Laya. It was a lovely discussion. Thank you all for making the time on a Friday afternoon to be here. And thank you to everyone for attending. We'll follow up after this with more information about the next C3 seminar.
Yes,
Thank you,
absolutely.
everyone.
Thank you very much, everyone. And we'll share the link of the recording with you guys too. Have a very good Friday evening. Bye-bye.
Thanks for having us.
Yes,
Take care.
thank you.
Thank you.
Bye, everyone.